Yeah, hello and welcome to the iTrain seminar number 19 on data combination. Let me just switch off my video to save some bandwidth. So, okay, so this talk is about data combination, and it's only an introduction. Of course, we can have more extended, more detailed discussions in later iTrain sessions. But in this introduction, I have kind of foreseen two parts. The first half is about reminding ourselves why data combination is needed. And the second half, in the second half, we are going to look into how ALMA users can actually perform data combination with standard methods. Okay, here we go. What is actually the root cause for the need for data combination? This plot is the usual UV coverage plot, which we have got used to in the age of ALMA. The radius of the outer edge here is related to the angular resolution of the observation, and the radius of the inner edge some kind of interesting. So the radius of the outer edge of this UV coverage plot shows us essentially the angular resolution of the smallest scale that we are sensitive to, and the radius of the inner edge shows us the largest scale. This inner edge is the radius of the shortest baseline, and that means we have not only outside of the outer edge no knowledge of the object, but also in this inner hole. This is the so-called shortest spacing problem. And furthermore, because we can't buy enough antennas, UV coverage between the edges is incomplete. So there are holes here all over the place. But the incompleteness of our knowledge of the emission at different angular scales goes even further. The outer and inner edge have essentially zero sensitivity. The true angular resolution is actually approximately determined by the L80, and the true maximum recoverable scale is determined by the L05, so by the 80th percentile of the baseline length distribution and the 5th percentile of the baseline length distribution. So the scale is computed by lambda over L05 or lambda over L80 for the smallest scale and lambda over L05 for the largest scale. This table from the ALMA technical handbook shows the minimum, maximum L05 and L80 baseline lengths for all nominal ALMA 43 antennas configurations. You can see that the minimum baseline of the 12-meter array actually remains constant at 15 meters up to config 6. So it's always the same up to here. And then starts to increase up to 244 meters for configuration 10. And the L05 goes up only slowly, and then reaches 1.2 kilometers at configuration 10. The L80, on the other hand, increases steadily from 160 meters in config 1 to 16 kilometers, meaning so 2 orders of magnitude increase in config 10. The 7-meter array has an L05 of 9 meters and an L80 of 31 meters. The angular resolution and maximum recoverable scale can be derived approximately by dividing the observation wavelengths by these values. the more exact calculation depends on the weighting scheme that you're using. And of course, all baseline lengths depend on the elevation and hour angle at which you're observing. So it's not a constant setup. See the ALMA technical handbook for more details. Now let's see what happens if we have or don't have these short baselines or short spacings. The scientific use case is typically similar to the following. We need to ask us the question, can we distinguish these two models with the given UV coverage of our interferometer? In particular, can we determine whether there is a more extended structure around this bright ring or not? So can we determine whether this bright structure here is actually there in reality or not? Now, the answer is, as you have probably expected, no. With the ALMA 12-meter UV coverage shown on slide 2 alone, it would be impossible to tell whether the extended structure is there or not. However, if we also observe with the ALMA 7-meter array, which has shorter baselines and partially fills the central hole in the UV coverage, and then combine this observation with our 12-meter data, we can see the extended structure very well. So here, this is a simulated combined 12 and 7-meter image. And yeah, the agreement with the original truth is quite good. Note that missing short spacings can also cause a non-Gaussian PSF, which in turn increases the noise correlation and the noise RMS in your images. So this is this white kind of diffuse structure that you can see here. Another reason to do data combination. So if you are planning an astronomical experiment with an interferometer, you should explore in which way the filtering of spatial scales affects your science case. Here a little demo from our ongoing development study. The synthetic image shows different groups of Gaussians in 7 different sizes and with 3 different brightness levels spread over an area of about 4 by 4 arc minutes. So if you would observe this with 115 gigahertz ALMA 12-meter array, this would require a mosaic with 75 fields. Now, if you simulate an observation of this field, or rather of these 75 fields with ALMA configuration 5, this is what we get. We can see that many structures appear less bright than they really are. So there's a loss of flux. Some structures change their morphology. For example, on the lower left, these two Gaussians have merged into one elliptical blob. These as well. Same happened also here and there. And other structures disappear completely. I mean, this whole group of Gaussians is essentially not visible anymore. On the other hand, non-physical structures appear. Some of them have negative fluxes. For example, here, this big trough, this thing down there shouldn't be there. Yeah, so there's this correlated noise that we mentioned earlier. To show you how big the danger really is, here another example, this time from real data taken with the SMA on the left and the ALMA 12-meter array on the right. This is taken from Wilner et al. The observed debris disk is well visible with the compact SMA interferometer, while the longer baseline observation with ALMA completely resolves it out. So although ALMA has nearly 5 times more antennas than the SMA here, the SMA image renders the overall structure of the object more accurately because its baselines have the right lengths. Now an example from our recent systematic study of data combination methods, which started at the workshop in Leiden in 2019, and which was published here in this paper, Plunkett et al. 2023. Shown on the left is a synthetic image with power at a large range of scales. To make the point that not only extended structures suffer, we zoom into the center, where there are some structures of the size of the synthesized beam. So this is the size of the synthesized beam, And here you can see various peaks in this input model that have about the same size. On the right now, you see what the ALMA 12-meter array would see. While the overall morphology is reasonably conserved, the entire image has massively lost flux. Also, the structures which are of the size of a synthesized beam have lost flux, even though they are essentially point sources. So even if you are only interested in point sources, you should also be interested in data combination if these point sources you're interested in are not isolated. In our study, we show that different data combination methods perform differently well in recovering our particular test image. But any method is better than no data combination at all. Here again, the 3 images from the previous slide, plus 3 more images, which shows a result of different data combination methods adding single dish data. This plot on the lower right then shows a profile of these images along a line through the bright point source. So I think it's roughly this profile here. Oh no, probably it's that one. Anyway, so you can see here in red what you get from the purely interferometric observation, and all the other lines except the dashed one are then results of data combination with single dish data with 3 different methods. You can see all of them perform much better than the pure interferometric observation and come actually very close to the shape of the true sky model. So anything is better than no data combination. Finally, for the spectrometrists, this slide also from our recent paper shows a spectrogram here, which is essentially a 2D histogram of the number of pixels which have a certain relative error with respect to the single dish flux. So this is real data, observations of M100 in a CO line or so. And this frequency of different relative errors is then shown versus the channel of the image cube. And you can see that the most probable relative error, which is already quite large, is not even constant with channel. It has this banana shape. So that means if you now start producing spectra using this image cube without data combination, you get a highly distorted spectrum. It's not just scaled down, but it's really distorted. So here again, the red line is without data combination, and the other 2 lines are with 2 different data combination methods, and the 2 different data combination methods agree quite well. While the purely interferometric observation produces a line shape that is systematically different. And here it even produces some kind of fake absorption line, which is really not there. So spectra without short spacings are not only scaled down, but can be heavily distorted. So it's clear now that every interferometric observation must include an analysis of the spatial filtering effects. And if we find that relevant angular scales are not observed with our one instrument, then we must get this information from other instruments and combine it with our original data set. This is, of course, not as simple as it sounds. First of all data sets to be combined need to be well flux calibrated, at least relative to each other. And secondly, you must make sure that your object is not time variable on timescales which are shorter than the time between your different observations to be combined. ALMA has been designed with all this in mind. And so we have a whole scheme of scheduling that is geared towards data combination. So ALMA was designed from the start to give users the ability to image all relevant angular scales within one project with good relative calibration and small time offsets. From the observation parameters which the PI provides in the proposal, DOT creates for each target a group of up to 4 scheduling blocks, or SBs. These are up to 2 12-meter SBs named TM1 and TM2. The TM2 is always the one with lower resolution, and if there's only one 12-meter SB, it's always named TM1. Plus up to one 7-meter SB and up to one total power or single dish SB. The member ops unit sets coming out of the executions of these scheduling blocks then form a so-called group ops unit set, or GOUS. And that is given its own unified identifier, or UID. And ALMA quality assurance produces images for all the MOUSs in the group. But so far, unfortunately, we have not tackled the combination question. So the combination of the MOUSs in the groups is still left to the ALMA users. This shows the possible non-trivial group MOUSs, so groups with more than one scheduling block in them. If your group does not have a total power SB, you can try to get approximate single-dish data, appropriate single-dish data from other observatories like the IRM 30-meter, for example. To combine the data from one group, 2 basic combination methods are needed. A combination of interferometric data from different arrays, so visibilities plus visibilities from 2 different setups. And B, combination of interferometric data with single dish data. And this second method can, in practice, also include the first one. So you can also combine several sets of visibilities or measurement sets with an image, if there's more than one. So let's first look at case A, the combination of different interferometric data sets. This is relatively simple, as it can be done within the usual T-clean task, and I'm sure many of you have already done this. Several measurement sets from different 12-meter observations of the same field can just be fed into T-clean as a list and then jointly deconvolved. If there's also 7-meter data involved, you need to use the gridder mosaic, even for a field, even for a single field observation. In order to take care of the heterogeneous dish diameter, this is necessary, and only gridder mosaic can do this at the moment. In all cases, you need to keep an eye on the quality of your point spread function. This can be done by looking at the so-called baseline length distribution, which is shown here in this plot at the bottom. A baseline length distribution is essentially a histogram of sensitivity or number of visibility entries in your measurement set as a function of baseline length. And this particular baseline length distribution here shows actually 2 baseline length distributions. The one in blue was obtained by combining a 2-hour observation with configuration 6 and a half-an-hour observation in configuration 3. For comparison, the green histogram shows the ideal baseline length distribution shape for a as Gaussian as possible point spread function with the same angular resolution and overall sensitivity as the blue shape. As you can see, the discrepancy is large. In some cases here, factor 2. And the larger this discrepancy, the less Gaussian will be your PSF. but there are good reasons to fight against this. So you should try to keep your PSF reasonably Gaussian in order to have more reliable image deconvolution, less artifacts from side lobes, and lower noise RMS in your final image after deconvolution. So this is an extreme example. In true ALMA observations, the groups are normally set up to have more reasonable relative observation times. So 2 hours and 0.5 would probably not be chosen. Now we come to the last section of the talk, which is on the combination of interferometric data with single dish data with CASA. Here we have 4 methods available. The first and most well-known one is Feather, which uses the CASA task of the same name, Feather. This method combines 2 images in the Fourier plane and is actually at the heart of all these methods except the last one, TP2Vis. TP2Vis works with pseudo-visibilities instead. And I will go through all these methods in more detail now. Feather is a well-established algorithm. It Fourier transforms the 2 input images and then adds the transform with a scale-dependent weighting and then transforms the sum back into image space. The relative scale of the Fourier amplitudes can be controlled via the parameter SD factor, which is 1 by default, and typically is chosen near 1, so the largest values I've seen were something like 1.2 or 1.5 or so. The shape of the weighting function, on the other hand, can be controlled by the parameter fdish_diam, effective dish diameter, and that has the constraint that it must be smaller than the true effective dish diameter, which in turn is derived from the primary beam of the single dish. And here is now a description of the typical procedure you should follow to feather 2 images. So first you T-clean all the interferometric data into one image or cube. Then you prepare the single dish image based on what you see in your interferometric image cube in terms of parameters of restoring beam, flux units, axis names, and axis units, and spectral grid. And you can use ImHat, ImMath, and ImRegrid to adjust all this until your SD image matches your int cube or int image. And at the end, you feather the int image and the SD image together. The actual call to feather is very short. It has only very few parameters. The high-res image, so the interferometric image, in the normal case, the low-res image, the single dish image, and then these 2 parameters that I've already mentioned. And there's a third one, which I will mention in a moment. And then, of course, the image name of the output image. So one can learn a lot about how feather works by playing with the CASA GUI tool called CASA Feather. This is, let's say, not very well maintained by now, but it still works. I just tested it, and it is a bit clunky, but I still recommend it as a learning tool. And shown here is now an example of this GUI output for a CO line observation in band 6 of some well-resolved galaxy with the 7-meter and the total power ALMA data set. The left axis here is a logarithmic axis, and it gives you the amplitude of the Fourier transform of the data. And you see here with this scale now the single dish Fourier amplitude in green and the 7-meter Fourier amplitude in purple, both after weighting. And the sum of the 2 is shown here in blue. On the right axis is the value of the orange and the yellow line, which show the weight for the 7-meter and for the single dish data. Vertical black line shows the location of the effective dish diameter of the single dish data. So that's 11.58 meters in this case, a little bit smaller than the physical dish diameter of the 12-meter total power dishes. The shortest 7-meter baseline is a little more than 7-meter long. And so this shaded region here, this blue shaded region, is where the two instruments both have significant UV coverage. Below this range, so here, only the single dish has sensitivity, and above the range here, only the 7-meter array has sensitivity. In spite of that, the 7-meter and the single dish images can still contain Fourier components outside their UV coverage range. These come from imaging artifacts. So, for example, here, all this shouldn't be there. They are very low amplitude, of course. Remember, this is log scale. But they can do something to the sum because the interferometric part is also quite low amplitude here. And you can try to suppress this using the low pass filter SD parameter. If you set this to true, it will try to suppress this somewhat. If we now zoom in on the region near the overlap in UV coverage, we can see that the other two parameters, F dish diam and SD factor, have the following effects. So the F dish diam parameter sets the point where the single dish weight drops below about 5% here, and where at the same time the interferometric data weight goes above 95%. On the other hand, the SD factor simply scales the single dish Fourier amplitudes by its value. So if we set SD factor from 1 to 2, then this green line simply goes up by a factor 2, but this is actually not so easily visible here because this is a log scale. But you can see it here. So these two dashed lines are in exactly the same location, and while the interferometric part has not moved, the green line has gone up. And also, of course, the sum of the two lines, the blue line, has gone up. We need to move on to the next method, model-assisted clean and feather. In our study, we also called this hybrid in Plunkett et al. To use this method, you proceed more or less as for pure feather, but you prepare the single dish image first and use it as a start model in the T-clean to create the interferometric image. This aids in performing the right masking and has other beneficial effects. At the end, you feather the resulting interferometric image with the SD image as before. A note concerning computing power needs. So most of the computing time goes in all these methods into the deconvolution, meaning into the cleaning, whereas the feather itself is relatively fast, depending, of course, on your image sizes. But even for cubes, we're talking about minutes. Coming now to the next and last feather-based method, SDInt is a algorithm that was documented by Rao, Naik, and Brown in 2019 in the AppJ letter or paper. I'm not sure it's a letter. And this algorithm has been implemented since CASA 6.1.1 in the CASA task SDInt imaging. This algorithm takes the model-assisted clean idea one step further and performs a feather at the end of each major cycle to obtain an updated residual cube for deconvolution. So here after obtaining the residual images for the individual components. They are feathered together to create the input for a normal deconvolution minor cycle, and various deconvolvers have been implemented here. I'll come back to this in a moment. And so this deconvolution runs as usual. And then when we come out again, the SD residual image is taken out here. And so the main changes are really only in the major cycle. And the whole scheme has the advantage that a better handling of the primary beam is possible. I have to refer you for more details to the paper by Rao et al. It's a very good read. You learn a lot about data combination there as well. Note that if you decide to work with SD-int imaging, you should start with CASA 6.6, which is going to be released very soon. And that contains a few improvements I had the pleasure to work on, in particular for single plane images. The typical procedure to follow when using SD-int imaging is to first decide on the details of the t-clean parameters by running t-clean on the interferometric data alone, and just producing a dirty image. Then prepare the matching single dish image as for feather or model-assisted clean feather, and finally run SD-int imaging with the interferometric measurement sets and the SD image as input. The parameters of SD-int imaging are nearly identical with those of t-clean, with some constraints. Plus, there are 5 additional parameters which handle essentially the special needs of this algorithm. So first of all, there's use data, which tells SD-int imaging whether we have single dish and interferometric data, or only single dish or only interferometric data. The settings SD and int are really only for testing. So for data combination, you need SD-int. Then the SD image, of course. Then the third thing is the image of the single dish PSF. That can be replaced by just giving the dish diameter, but you need to give one of the two. So either the PSF or just the dish diameter. And then finally, there's something similar to SD factor called SD gain, but it's not quite the same as SD factor. This SD gain deserves special attention, and it has a more tricky initial choice. So here, some theoretical considerations suggest that a good choice is probably to take SD gain as equal to the ratio of the interferometric and the total power RMS squared. But to compute this ratio, of course, you need to bring those two RMS values to the same unit. So for example, the Jansky per stair radian or something like this. So not Jansky per beam, because the beams are different. So for example, for an ALMA 7 meter plus total power observation here, any numerical example. So we have here in the interferometric image 0.1 Jansky per beam, in the total power image 0.64 Jansky per beam noise. RMS, both of course has to be in the same bandwidth, but the beam areas are significantly different. So converting these two values to Jansky per stair radian, we finally obtain then a suggested SD gain value of 7.2, which seems large, but in the test in question, it actually really gave very reasonably looking images. But there hasn't been a detailed study yet with simulations. And now here the constraints on the T-clean parameters in SD-int imaging validated have been the following combinations of options for the deconvolution. So in spec mode cube, so in cube imaging, you can use the deconvolver's multiscale or Hogbohm with the grid as standard or mosaic. And you can do this both with parallel or non-parallel processing. And if you only process a single plane image, you need to use spec mode MFS as usual. And here only the deconvolver MT MFS will work, and that only with n terms equals 1. So not really multi-term, but never mind. And here you can use the same grid as again standard in mosaic and also in parallel or not. The last method I want to mention is dp2vis. This is nicely documented on this GitHub page, and I really need to refer you to the details to that page, because in our study, in the Plunkett et al. Paper, we were not really able to use this with CASA 6. But I've talked to the authors of dp2vis, and they are working on a new release that will work on CASA 6 and has various improvements. So watch that space. It is definitely a very promising approach. And here, the main control parameter actually is also related to the total power sensitivity. So it's the total power RMS estimate. But yeah, please refer to that GitHub page. So that brings me to the end of the talk. I think I've stayed within the time. So to summarize, all users of interferometers should verify if they need to improve their images by combining their high-resolution visibilities with shorter spacing data or with SD images. You can get this shorter spacing data already often from your own group OUS. If not, you can take it from other observatories. The combination of different interferometer arrays can be done already with T-clean alone. And for data combination with single dish data, there are essentially 3 main feather-based methods. Feather itself is model-assisted clean, and feather and SD-int that are now mature enough to use them also for publications, I would say. And then there's this other promising approach, dp2vis, which hopefully will be soon available for CASA 6. In our study, which was published earlier this year, we found that actually this model-assisted clean plus feather and SD-int were the 2 methods that performed best in terms of image fidelity. So those are probably the ones I would recommend now, but anything is better than not doing combination at all if you have extended objects / diffuse emission in your image. And yeah, there is much more to tuning the performance of your data combination parameters and also measuring the performance of your data combination. And I hope we can organize another iTrain session to discuss this in more detail. Thank you very much for your attention.